Good afternoon, Black Hat. Thanks for being here. Obligatory background slide. If you don't know me, I work for Google on the Project Zero research team, specializing in Windows, mainly privilege escalation sort of vulnerabilities, mainly because I like logical vulnerabilities and rather than memory corruption. So I find that quite often in these sort of types of things. So what exactly am I going to talk about? So this will be quite a technical talk. It's a talk for people who want to hunt for bugs in the Windows kernel. And it's specifically related to the Windows security, access security mechanisms, and how it relates to how kernel code and kernel drivers may actually interact with the Windows security mechanism to verify a user's identity. Now, Windows is actually a reasonably complicated sort of security architecture, but you can actually sort of break it down to sort of three main parts. The first part is each resource, say a file or a process, has some sort of security associated with it, which defines who is allowed to access it and what they're allowed to do once they do access it. This is stored in something called a security descriptor and contains various bits of information about the securable resource and what you're allowed to do with it. The next component is the process, and specifically its associated access token. And the access token is your user identity, effectively. It provides the identity to the operating system. And these two combine when you do system calls or other kernel and driver code gets involved and talks to something called the security reference monitor. And the security reference monitor is responsible for actually enforcing the security of the system and providing security decisions. So you can find documentation about the SRM, the security reference monitor. Basically, if you're doing kernel mode code, if the function starts with the prefix SE, that means it's something related to security. Now, the real core of pretty much all security decisions is the access check, and this is done usually through a function called SE access check. And effectively, it's just sort of taking your token and applying it to your security descriptor and making a decision on whether I'm going to give you access or not. So there's a few different steps. The first step being checking what is called the integrity level. And the integrity level is something they added in Vista, which it's like a mandatory access control mechanism. It's simply a number. Your access token has a number. The resource has a number. And if you are above or equal to the resource number, you're allowed access. Otherwise, it can tell you to go away. Then it goes into things like owner check, but then the DACL check is the most important part. This is where it determines what you can actually do with that resource. If that succeeds, you've got access. If it doesn't, it'll tell you to go away. Now, the access token is actually a pretty complicated structure. So if you think of a sort of traditional Unix system, you may have had user IDs or group IDs, just sort of simple numeric values. But the access token in Windows uses something called the security identifier, which is actually a sort of more complicated structure. This is this S and multiple sort of numbers after it. Now, it also contains things like your groups. So you have your user, it has your groups. It has your mandatory label. This is your integrity level. And it also has privileges, which I'll go into a little bit briefly at the end because it has important consequences elsewhere. But fundamentally, your access token is just another kernel object. It's just another allocated buffer in memory, allocated structure in kernel memory, which has some values in it. And obviously it has then a similar association with all other sort of types of kernel objects, including it can actually be securable. It can have its own security descriptor and access control list, and which defines who can access that token information. Now, it wouldn't be, obviously, it's too simple if it was just a single type of token, because obviously there's many sort of scenarios in which you may find yourself. So I've kind of broken this down into sort of four main types of tokens. You could probably argue for different sort of categorization. But the sort of main one you would normally see, the normal token, is just the one you would run as a normal user. You'd have your normal basic token. Now, when you get UAC involved, user account control, you may also have something called a linked token. And this is just another token which is associated with the same token. So for example, you could have an administrator token linked to your normal user token, and potentially you can switch between them by talking to the appropriate service. Now underneath normal tokens, you have two system calls which allow you to create sort of new tokens with new security properties. You have first NT filter token. This creates what is called a filter token, and you actually also see this referred to as a restricted token because of the Win32 API calls it the create restricted token. Now in Windows 8, to support app containers and the sort of immersive applications, a new type of token was created, the lowbox token, and then there's an appropriate function to call. But both of those functions take an existing token and effectively copy some of its security information and imply new sort of security categorizations. So there's loads of important fields you need to bear in mind when sort of thinking about token security. Obviously, you've got your groups, your user, but you also got things like your token ID, which is a unique 64-bit number. It's basically an incrementing number which is assigned to each token. It's only locally unique, but that's all that matters. Counterpart to that, you have the parent token ID, and this is used sometimes for security decisions, and just reflects, say, when you're doing a filtered token, reflects which token you created that token from. And then various other sort of things in there. Now, in common with all kernel objects, or pretty much all kernel objects, you can actually access it from user mode. There are system calls to get hold of access tokens and manipulate them. So when you do that, you get hold of a handle to that kernel object, because obviously user mode can't talk to the pointer directly. And it has certain access rights which you can get access to. And these are sort of the important ones to bear in mind when you're sort of looking at token work. Things like, can I duplicate the token? Can I assign it as a new token for a new process? Or can I impersonate that token? And if you don't have these rights, then you can't actually perform that action. And that can become quite important for certain sort of events. Now, I categorized 4 sort of types of tokens. But of course, that's still not the end of the story. There's actually 2 types of each type of token. They're just simple values which are part of the token structure itself. And the first type is the primary token. This is the token you assign to a process, the main token for that process. The other token is impersonation tokens. And impersonation tokens are used to allow for impersonating another user. And you can think of impersonation in the sort of context of a secure service. Like a high privilege service may want to do something on behalf of that user, which is calling it, which would probably be just a normal user. Now, it could go through some convoluted process, pulling out your username, manually verifying whether you're allowed to access a resource. But it'd be far easier to just actually say, I'm going to pretend to be you for a few minutes or a few seconds, and I'm going to perform those actions as if I was you. And this is where impersonation tokens come in. They're assigned to a single thread, so when you're running in that thread, it can potentially perform any action that user would normally be able to do. And the impersonation token, when set, actually takes primacy over the primary token, so it will actually ignore your current token. Now, impersonation tokens then have 4 kind of categories of token. So we've got even more tokens. And this is related to the impersonation level. And this is something which basically sort of determines what you're allowed to do with that token. So the top 2, delegation and impersonation, are, from a local perspective, exactly the same thing. There's no actual difference between the 2. But what actually happens is, if you've got delegation or impersonation level, you can pretend to be that user from a security perspective. However, if you've got less than that, if you've got, say, identification level, all you can do is sort of read out the information about that user and that token, but you can't actually use it for security work. You can't open a file under that user's context. It just won't allow you to do it. Now, the reason that there is a difference between delegation and impersonation, but not locally, is delegation is used for allowing delegating your credentials to remote systems. But you have to set that up. You're usually in a domain, so we don't actually have to care about it. Now, when you want to convert between a primary token and an impersonation token, one thing you can do is duplicate that token. And there's a system call to do this for you. You need the token duplicate access right, but one thing you can do, if you have access to a primary token, you can always convert it to an equivalent impersonation token. However, for security reasons, you can't convert back unless the level is greater or equal to impersonate. And you can kind of understand why. If you could convert an identification token back, then you could potentially create a new process as that user and pretend to be that user. And you don't want that to happen. And also, each new token you get gets created with a new unique identifier. So yeah, it's worth keeping track of that. So you can set it in various ways. There's a direct setting mechanism, sort of an explicit setting, where you actually have a handle to a token, and you say, set this token on this thread. But there's also indirect mechanisms. So this is where effectively the kernel has some sort of reference to a security context, say a named pipe client or a RPC client, and you say, I want to impersonate the person who called my service. And so this allows you to sort of transit security credentials between two different processes. And then the kernel has a few extra functions to do basically the same thing. That'll be a real problem if normal users could impersonate any other user. If they just had a handle to a token, they could pretend to be local system, that would be bad. So there is actually some security involved. So prior to Windows 2000, this thing didn't really exist. But after that, a new privilege was added, impersonate privilege. And unless you have that, you're very restricted on what type of token you can impersonate. Specifically, you can't impersonate a token which has a higher integrity level than you are, because that would be a security problem. You also can only impersonate a token which has the same user ID as you. Seems reasonable. But crucially, this is not a hard fail. When you call setThreadToken, it doesn't just say access denied. Instead, it will actually still set the token, but it will recreate it and set it to identification level. And this is actually quite important for the sort of topic of my talk. So there's a few things you can do with that. You can do your normal access checks. There is system calls to do access checks, which work with identification tokens. But in the kernel, it should never, ever treat an identification token as valid. So this is why I call it social engineering. Effectively, you are it's really easy to get hold of this identification token for all intents and purposes. And from a kernel perspective, it looks almost exactly the same. There's like only 2 bits difference between a actual valid impersonation token and an identification token. So if you can get hold of these tokens, maybe you can actually pretend to be someone you're not. And if the gatekeeper, the guy in the kernel who's actually like verifying your identity, doesn't check correctly your token, maybe you can do something more serious. Okay. So if you need to actually exploit token vulnerabilities, the first thing you need to do is be able to capture them in the first place. And that might seem actually quite a difficult thing to do, but it turns out it's actually pretty easy. You can go the logon user route. So there's a function to log on a user. If you know their password, you can just log them on. But of course, if you do that, you already know their password and you can probably do more serious stuff. If you're using UAC and the vulnerability you find requires an administrator token, there's a system call to just get you back an identification level impersonation token for the UAC user. And I'll just return you, and you can do that from any privilege level. Even like sort of super sandbox Chrome renderer, you can still call this system call and get back a token which represents the admin. A classic attack is named pipes. So if you've read any of the work of things like token kidnapping or access to like pre-Windows 2000 privilege escalation, named pipes come up quite a lot because they're really easy and by default, will always open, like they'll usually allow you to get a impersonation token off them if someone at a higher privilege level or a different user opens that named pipe endpoint. So we can get, say, Windows Defender to scan our pipe name. It doesn't know any better. It calls it as local system, and we've got our local system identification token. Similar with RPC and DCOM especially, because it has loads of callback mechanisms, and there's a function to get impersonation there. Another interesting one is NTLM negotiation. NTLM, it has system calls on the machine to negotiate a impersonation token. If you can get a local service to negotiate, say, WebDAV to you, you can then do NTLM, and you can get a local system token that way. And finally, my favorite one, like just because it seems so ridiculous, is there's a system called Services for User. And this is kind of for Kerberos support. It basically allows you to create like services under certain user accounts. And it turns out, at least on Windows 8.1, you can call a function to create this, specify any local or even domain user, and it will hand you back an identification token of that user. That's kind of useful. Of course, you can't get a full impersonation token, but an identification token could be sufficient. So I'm going to show you a little demo of a tool I've written, which I hope to release after the conference, which actually just does a few sort of like playing around with tokens, viewing token information. So let me just run that. Yeah. Okay. Okay. So, for example, you can look at just like processes. So there's loads of like existing processes you can open, and it will show you like obviously your user SID, your token type, so in this case it's obviously primary token because it's coming off a process. Oops. But obviously we want to do sort of fun stuff like this. So I've enabled the administrator account on the local machine. I don't know his password because I'm not the administrator, obviously. So as long as I can type his name correctly, I should be able to create that, and I get the local administrator with an identification token. It just says, here we go, have your token. And so there's a few others. For example, if I want to get a local system token, I can use the COM reflection tricks, basically. One of them I use is the bit service, which is used for HTTP transfers. You click that, and you get, obviously, local system, identification token out of it, and using COM reflection and stuff. Okay. So now let's actually go into sort of examples of vulnerabilities I've found or other people have found, which you can actually, if you can find these types of bugs, you can actually exploit them using this fake ID, this identification token tricks. Oops. So the first thing before you can actually look for these bugs is understand how kernel mode code and the kernel itself interacts with tokens. So there's various process and thread manager calls, such as reference primary token, reference impersonation token, and they take like a pointer to the process or pointer to a thread and return you back that information. There's also system calls, which are supposed to be used from user mode, but can be used from kernel mode if you like. And if you're the kernel itself, obviously this isn't recommended if you're a driver, you can actually just access the token data directly via its thread pointer or its process pointer. And finally, the I/O manager will actually capture the security context of which is being called when you try and open, say, a device or a file, and it will actually hand that to you as part of the IRP create call. So this is the first, probably most obvious bug you can think of. We've got this identification mechanism. We've got this impersonation level. What if the code forgets to check the impersonation level? That would be an obvious bug. Okay, so in this case, when you actually do an SE access check, there's a special structure called a security subject context, which is normally used, which contains both a reference to the current thread token, if there is one, or it's null, or the primary token. And the primary token should always be there. Now, as part of the sort of NT driver development kit headers, there's then a define called SE query subject context token, which just does a simple sort of if statement. It says, if we've got a client token, return client token, otherwise return primary token. But the trouble with this is it really hides the sort of context of the actual token operation, which token you're looking at. So if code just does this blindly, and it may forget that it could actually be getting the impersonation token, not the primary token, and therefore needs to check the impersonation level. And there's a few variants of this using some of the other functions you can find, but they're basically the same bug. So a real example was this. So this is in the application help cache. It was actually a Windows 8.1 specific vulnerability or Windows 8 specific vulnerability. And it was doing a check to whether the current caller was an administrator or it was local system. And literally all it did was it got the impersonation token and forgot to check the impersonation level. So as long as I could get a local system token at an identification level, which I've just demonstrated I can do very easily, you could pretend to be an administrator. And that allows you to then fill up the application compatibility cache with some malicious entries, which then allows you to do a sort of privilege escalation attack. Now, there was a second function there, this SE token is admin. And actually, it turns out that prior to Windows 8, this also does not actually do any verification of the token you pass it. So if you pass an identification token to this function, and this isn't documented, mind, it will actually say, yeah, well, it has the admin group, so it must be an administrator. In Windows 8.1, possibly is something to do with the app container support, it actually does a verification check on the impersonation level now. So this would be vulnerable on Win 7, but not on Win 8. Now, another bug is related to that security subject context in a different way. I showed at the start there was like a token class, token structure, which represented the token kernel object. Now, that's actually obviously internal to Windows, it's internal to the kernel, and is not exposed through the development kit at all. Instead, it refers to access tokens used as p-access token pointer, and it's just an opaque pointer at this point. But security subject context isn't an opaque pointer. It has to be a defined structure because you have to actually access its members. So if you're trying to call a function like SE access check and you need this subject context, but you've only got a handle to a token, maybe you'll just go, well, we can just munge them in and it'll be fine, like, it'll all work. So if you set the primary token here, it basically screws SE access check's logic. It never checks the impersonation level because it never thinks you're actually impersonating. And because the two tokens are almost exactly the same, no one ever then verifies that you've not passed it an impersonation token incorrectly. So you can bypass it that. So this is a simple example in Windows 8 kernel. It's allowing access to an atom if you're running in a low box. And it just crafts a subject context and does an SE access check. And potentially you can bypass this. I've not reported this to Microsoft because I don't think there's actually a security implication. This is something to bear in mind with these bugs. Just because you can bypass a check doesn't mean you can actually do something useful with it. So a few others. So system thread impersonation. I showed that impersonation works if you have impersonation privilege. But if the code spins up, say, a worker thread in the system process, that implicitly has impersonate privilege. So you can impersonate tokens that you shouldn't normally be able to access and potentially get a system worker thread to do actions under, say, local system. Now, by far, I think one of the most interesting bugs I found was what I refer to as leaky tokens. So a token, as I've said, is just another kernel object. There's nothing stopping some other kernel component getting a reference to the pointer to that kernel object and handing back arbitrary handles to it, which shouldn't normally happen. But it obviously can. And if you can find this, you can potentially get access to tokens you really should not be able to access. So an example I found in Win32k, in Windows, I think it was Windows 8.1, they introduced this new system call, and let's face it, Win32k needs all the more vulnerable system calls it can get because it doesn't have enough already. It has this user get clipboard token call. And what it does is the last process to write to the clipboard, it will capture its subject context, it will capture the access token used in that scenario, and then another process can ask for it back and get a handle to it. And this has some interesting implications. Because the way in which the integrity level mechanism works, I can't open a process if I have a lower integrity level than the process has. So I can't read out its primary token. And that's just a byproduct of processes. You're not allowed read accesses to processes. However, you can get read access to tokens because no one assumed you can get access to a token outside of opening the process in the first place. So you can open it for read access, and read access gives you token duplicate access right, at which point you can convert this into any other token you like, gain any other privileges. If you lower the IL, you can then do some fun stuff, impersonate that token, and do some privilege escalation. So I'm going to quickly demo this. So if I bring up, say, Notepad, and just type some stuff in and copy it, so Win32k has now captured Notepad's primary token. And I can see that by going into here, and I've just got a button to bring that up. So that. You can trust me, that is Notepad's primary token. But that in itself doesn't sound actually that useful. But what if, for example, we had UAC getting involved? So let's say we close that down. Yeah. Let's create Notepad as administrator. Okay, so you type some stuff, and you copy that, and we click this again, and we now see we have the primary token of the administrator because it's running at high integrity level, and we can see in the groups that it's got administrator group. Okay. And this is actually like the actual primary token. So we've got a reference to an administrator's primary token, which we shouldn't normally be able to do. But we can't obviously use that. Say, for example, we have this. So I've just got a little sort of test. It impersonates the token, tries to create a file. If I try that, it's going to tell me access denied. Or in this case, you haven't got the required impersonation level. Because we failed that can I assign this impersonation token test? And so it's dropped it back to an identification token. However, we can duplicate it. We have read access, so we can actually change this token. So we can create an impersonation token, but change the IL to medium. And based on our security, the only thing we need to do is bypass that, because the user is still the same user, because this is UAC. So we duplicate that. We can see it says medium impersonation. Now if we go into this operation, so hello black hat, we can click create, and we have success because we've impersonated that token at medium, which is fine, and we've got the administrators group, so we should have test.txt. And that actually, so that Microsoft did fix this, but only from if you're going from low integrity to medium integrity, not from medium to high, because it's a UAC bypass, and therefore it's not going to get fixed. That's why I can do it on Windows 10, you see. So there's many more sort of different types of bugs you can find if you actually go looking. And this one was something related to duplication in the kernel. When you call ntDuplicate token, to duplicate a new copy of a token, it does a check to make sure that the token you're passing is valid to convert into that other token type. So this comes down to you can't take an identification token, convert to a primary token. But if kernel code calls the internal duplicate token function, SEP duplicate token, that check is bypassed. This is only in like this sort of user level sort of like exposed functionality. But if the kernel does it, it can convert it to any token you like. So a real world example is this one. It's abusing create process as user. So create process as user allows you to create a new process with a different primary token. And if you read the documentation, it explicitly pretty much says you need a handle to the primary token in order to create this new process. So if you actually go digging, it turns out that when it opens the handle, you just need token assigned primary privilege. And strangely enough, even though you've got say you've got an identification token, even though it's not a primary token, you can still get token assigned primary privilege in your handle, so you can bypass this check. And then when it actually goes to create it, it calls this internal duplicate function. But no one ever verified that this token was compatible to convert back into a primary token. So we've got a problem. We can potentially spawn processes using only identification tokens. Now, the actual limit of exploitability depends on who you are. If you're a system service, you've probably got assigned primary token privilege. That means you can assign any token. So you can use it in the old sort of token kidnapping tricks. You get an identification token. You can't impersonate it to elevate to that user, but you can create a new process as local system. But you can also do it from lower privileged processes. And to understand why, you have to kind of see how it determines whether you're allowed to assign a token or not to a process. And it's actually based on either a parental or a sibling relationship between the tokens. When you create, say, a filtered token, the token ID is copied into the new token's parent token ID. And if you've got that relationship between the current process token and the new token you're trying to assign, it will allow it. Otherwise, if it's a sibling token, if it's both crafted from the same token and within the same authentication ID, so the same login session, it will also allow it. And this is the case for duplicate token or create lowbox token. And the lowbox token thing is quite important because what it means is you can use it to effectively break out of enhanced protected mode in IE. Because IE uses the lowbox token to secure its rendering processes. If you can do things like a named pipe attack, you can get the identification token for the normal user. And as far as the kernel is concerned, the normal user token is a sibling of the IE EPM lowbox token. So even though you've only got identification level, you can create a new process, and the only thing you've got to do is drop the integrity level. So effectively you get a new process running at low, but outside of EPM. And Microsoft, again, don't particularly consider the equivalent of IE protected mode, which isn't generally considered to be a security boundary. So effectively, you can get out of a partial break of the sandbox, and then you can potentially do something else to fully break out of the sandbox. Now, one of the sort of more surprising bugs is relating to sort of timer check time of use, because impersonation tokens are assigned to threads. But unless that thread object is locked, you can change the token while the kernel is doing operations. So you can get it to do one check, and then actually change the token in another thread, and then get it to do another check. And this can be while it's still running inside kernel mode. And it's kind of a simple trick to do. But you can also do it in scenarios such as the I/O manager. So the I/O manager only verifies the security of the caller when you open the file, not when you do things like device I/O control. So you can actually open a file with one user context, call device I/O control with a different user context, and it gets confused. And an example of that is this one in the WebDAV driver, which basically allows you to access functionality which you shouldn't normally be able to do. And all you need to do, again, is get a local system impersonation token, identification token. And that's all you need to do. Well, it makes it sound so simple. So, yeah, because WebDAV is actually more implemented in user mode, the kernel mode component actually only acts as a bridge between UNC pass, UNC shares, and the user mode service, which is actually doing things like the web requests and things like that. So this is why you can actually abuse this and pretend to be the WebDAV service and get it to do things that the Windows kernel doesn't actually expect to be able to do. And I think the final actual bug is be very mindful if you see any kernel code opening thread tokens using the system call variants. So there's two versions of these system calls. There's the normal open thread token, and then there's the open thread token EX. And the EX variant, I think, was introduced in Windows 2000 because there was actually a really fundamental bug from a kernel perspective in these functions. And that bug was basically, there's no way of specifying you want to open a kernel handle instead of a user handle. So if you find a driver which opens a token using one of these calls inside the context of your process, it will create a handle to that token, which you may not normally be able to access because the ZW system calls effectively bypass security. Now, you shouldn't see them, but I actually did a run-through of... So what I actually did when I did my research for this, I actually went on VirusTotal. And I have an account on VirusTotal, which allowed me to get, say, the top 10,000 Windows drivers out of VirusTotal. Obviously non-malicious. I didn't want to actually look at clearly malicious code, but supposedly benign Windows drivers. And then I wrote some basic static analysis tools to go hunting for these function calls, these sort of kernel interactions with tokens. And quite a few drivers still ended up with these tokens being there and actually trying to open tokens within the user context. And you shouldn't be allowed to do it, but apparently people still do. So coming towards the end, I'm going to talk about some changes. So obviously I found these bugs as part of Project Zero. Also at the same time, somehow coincidentally, Alex Ionescu started finding similar bugs in token handling. Completely not talking to each other about it at all, and somehow came to the sort of same conclusion. There was probably problems with token handling. So I think Microsoft have been doing some various fixes, various changes to different components of the operating system and the kernel to make it a bit more robust in these sort of scenarios. So I'm just going to go through a few things which have changed, specifically mainly focusing on Windows 10, because there's some interesting changes in there which may affect some of the sort of demonstrations I've already done. Now the first one is SE token is admin has been fixed in Windows 7. This is something I did not expect because it's kind of it's like backporting like security fixes which have been in Windows 8. So they've actually backported it. Now I think it wasn't necessarily my bugs which I sent them which actually prompted them to fix it. I actually found a bug in the NVIDIA display driver, like that classic get the reference the impersonation token, if not reference the primary token. Token is admin, and basically he was using it as an access check for whether you're allowed to do administrative functions in the driver. Now I'm of the suspecting belief that they may have influenced Microsoft more to fix this down level in Windows 7 than I probably did, but that of course is speculation. Now Windows 10 introduces some interesting changes to the actual security function which determines whether you're allowed to impersonate a token. And strangely enough, out of the two things they've added, one of them is actually sort of almost weakening impersonation. They've added new mechanisms to determine whether you're allowed to impersonate a token or not. But on the other hand, there's a check in there which would actually mitigate that demonstration I actually showed where you could impersonate an administrative token. So yeah, the first one is they've added a new capability. This is either through a user group or a low-box token capability, SID, which determines whether you're allowed to impersonate certain tokens. Probably the most interesting one is the sort of the first one in that list. Basically, it says if you've got this group and crucially a kernel flag has been set, you can impersonate any token at the same IAL level in the same session as you. And you kind of could do that anyway, but this kind of adds a new sort of variant. If a different user ends up on your session, potentially you can still impersonate that user. But fortunately, it's guarded behind a group. And the only way to get that group is to have admin access to add you to the group, which allows you to potentially get admin access. So it's not likely to be exploited, but I suppose you never know. If it's something which is valuable to enterprise administrator, he may enable it for everyone in the domain, because why not? I'm sure it'll be fine. Now, there's a few different known ones you can do sort of related to low-box tokens. So low-box, as I say, is the app container model, and it allows you to effectively add capabilities to applications in the Windows Store, which says they can actually do impersonation of certain types of tokens. That's kind of interesting. But I'm not actually seeing this used anywhere. So I'm not actually really sure why it's there yet. I'm sure at some point it will be documented or there'll be some sort of demonstration of why we're actually using this. But until that point, I just don't know. Now, the only other difference is elevated token protection. So my demonstration was, as long as I could get access to, say, the primary token from a administrator level process, I could lower the IL level quite easily and impersonate that user and get admin rights. Now, when you get that token, there's a flag which says, I am the elevated token. And there is a function in the kernel, se_token is elevated, to tell you whether an access token you've got happens to be elevated or not. So effectively, all this check does is it says, is there a mismatch between the token you're trying to impersonate and the primary token of your process? And if there is this mismatch, it's going to return you privilege not held. It's going to tell you you're not allowed to access that, at which point it will downgrade to an identification token, but that's roughly equivalent to not allowing you impersonation. But strangely enough, it's actually guarded behind a compatibility flag. Unless you set the kernel flag in the registry to enable this support, it will actually not protect by default. And that's obviously why I could still demonstrate on Windows 10 that same attack, because it's not actually on by default. But it's interesting thinking, like obviously it's an interesting attack vector, but obviously it's UAC. UAC is not usually considered a problem, a security boundary worth defending. So I suppose it may get turned on eventually. I don't know. So this is the sort of end of my talk. So just some sort of basic conclusions. The first thing to bear in mind is it is trivial to get an identification token. And if you use things like services for user, it's almost trivial to get an identification token for any user on the entire domain that you're connected to. And that's pretty powerful primitive if you can find the bugs, the appropriate bugs to actually exploit. If you're actually going hunting for stuff, if you find a driver which opens access tokens, it calls capture subject context, it calls reference impersonation token or reference primary token. If you see those calls, it's obviously doing some sort of personal security checks. Now, if you do not see SE access check imported, you would be right to be suspicious. There may be something of use there. Now, sometimes you'll see this, and it is completely benign. For example, I think the process monitors driver does this, but it's only doing it so it can record who is supposedly opening that file. So it uses this to basically extract your user identity and determine that you are Bob Smith. That's all it does it for. Now, of course, you could spoof that, but you shouldn't be relying on Process Monitor as your security auditing solution for your enterprise. But it's possible that there is a more serious bug there. And finally, never forget about timer check, timer use, even on the same thread, because you can switch threads arbitrarily. And there's a good sort of bug, I think, in the Project Zero tracker, if you go and hunt for it, where basically I could change a token during a registry open call and get it to write to the wrong registry hive, because basically it sort of redirected it to a different user's hive and actually do privilege escalation in that way. So thanks very much for listening through my talk, and yeah, thanks very much.